Okay, good afternoon. All right, so today we'll have a revision come tutorial of the inelastic neutron scattering. Okay, well, this is again quite known to you. That you need to know that the wave vector is 2 pi by lambda. The neutron energy is simply like for a classical particle, because these energies are quite low, and the velocities of these neutrons are pretty small. Yeah, just a minute. So the velocities of neutrons are typically a kilometer per second. So these are not relativistic particles. And so the energy is momentum square divided by the price of the mass. So it is h cross 2 lambda square. Numerically, for a lambda of around 1 angstrom, the energy is about 80 million joules. Okay, to get the numbers in perspective, this is what we have. We've already talked about it. So we'll come back to it if required. So typically for the frequency of 1 terahertz or angular frequency of 5 terahertz, the energy is around 4 billion joules. And in centimeter inverse units, this is about 33 centimeter units. Okay. As far as the theoretical formalism of lattice dynamics goes, here we have the concept of phonons when the vibrational amplitudes are small. So these are the mean positions of the atom K in a unit cell L. You can say L1, L2, L3, three indices of a unit cell, and an atom K. And the vibrational amplitude, the vibration, which is a time-dependent number, is this, and this is the actual position. Okay. So for a wave-like solution, we do express it as the displacement during the vibrations in a given direction alpha is as an amplitude and a phase factor. Now here, I would like to just tell one thing, that this equation is sometimes expressed slightly differently, in the sense that the phase factor often here I have used a convention in which the phase factor also has the atomic position within the unit cell, whereas alternatively, it will use it only the position of the unit cell and not the atomic positions, and that phase corresponding to the atomic position is absorbed in this prefactor. However, we'll continue to use this. This has a small effect in the form factors, the way they are defined. I'll come back to it if required. So, okay, just to revise, we have 3n for given n number of n atoms in the primitive cell or unit cell, actually primitive cell only. We have 3n eigenvalues, so these are the 3n angular frequencies and 3n displacement vectors corresponding to every phenomenon. And there are again, this is a wave vector dependent. These are all wave vector dependent as well. So depending on what is the wave vector, you have different frequencies and different displacement vectors. Okay, we had the density of states done. Okay, so now the dynamical structure factor is written like this. It has a phonon population factor as a very important term. So depending on the phonon population, the intensity is proportional to that. For neutron energy loss, it is n plus 1. For neutron energy gain, it is n. and these are the terms corresponding to the conservation of the wave vector and of the energy. Yeah. So now that is the one phonon. This term was not the way it is here. The actual position of the atom within the unit cell. However, if the only the unit cell center is used here, sorry, unit cell origin is one phonon structure factors. If you pick up the phonon structure, phonon eigenvectors from certain calculation, please ensure that what is the expression for the displacement terms used in terms of the eigenvectors, and then accordingly use this expression. So actually, because that phase is already included there in that expression, here it is only G. Okay, otherwise it would have been capital Q. Okay, so that's a small. Can be measured. Okay. So this is neutron spectrometer, where you have the crystals used to choose the value of the incident neutron energy or wavelength, as well as the value of the scattered neutron energy and wavelength. Resolution. Fine. So this is a new slide I have introduced. What are the steps in a single crystal phonon experiment? These are very important steps. So suppose you wish to make measurements of the phonon, individual phonons in a neutron scattering experiment using a single crystal. Well, quite often, as I said, you might be interested in a large number of phonons or a specific zone. In either case, these are the few steps that important steps that we need to look at. First thing is what is the temperature of measurement? The temperature was you might be interested in temperature dependence of phonon frequencies, but even if you are not, it is usually advisable to use a low temperature. If it's possible, you can use a cryostat and put your crystal into that. Why a low temperature is better? For one simple reason that the concept of phonon itself is more appropriate at lower temperature because the atomic displacements will be small, and so the phonons are more likely to be harmonic phonons with very small or very large lifetime and correspondingly very sharp in energy. And therefore, if you have a large number of phonons at nearby frequencies, it would be easier to identify them or separate them. Otherwise, the neighboring phonon peaks might overlap and it might be difficult to get proper frequencies. So generally, lower the temperature, it is better for the measurement of phonon dispersion curves. And quite often, one uses typically liquid nitrogen temperature. See it again, how much is low enough? Typically, you know what the Debye temperature of the material is. Debye temperature typically gives you the average frequency in a solid, and correspondingly you have a Debye energy H cross of omega, omega being the, let's say, the Debye frequency, And so we would like to, if the temperature is smaller, as much as the temperature than the Debye temperature, then you are better off. At high enough temperature, you begin getting a large amount of enharmonic interactions, and therefore phonon-phonon scattering, phonons being broad, and so on and so forth. Okay, that's fine. Second is then I need to choose what is the resolution for the measurements. It again depends on individual materials. As we said, if you have a crystal in which the atomic bonding is relatively weak, for example, van der Waals bonding, then the phonon frequencies themselves will be small, and there will be neighboring branches. Also, you need a higher resolution there. On the other hand, if you have a very strong bonding and consequently very large phonon frequencies and large phonon energies, then even a poorer resolution, you will be able to identify those phonons. So, typically, one has to be aware of what is the resolution required and accordingly choose an instrument and also choose instrument settings because even in a given instrument, the resolution strongly depends on what are the incident energies or the scattered neutron energies, what are the Bragg angles of the monochromator and analyzer, or if it's a time of flight spectrometer, then what are the various what is the flight length, time of okay, total distance over this neutron travels, what are the average energies again, what is the flight time, what is the resolution of the electronics, which measures the flight time, and so on and so forth. So resolution is a very important consideration in making measurements. Again, you would know what is the change in frequency. For example, if you're trying to measure the changes in frequencies as a function of uh, temperature or pressure or any quantity, then you know what kind of changes actually take place or are expected to take place based on various predictions. There might be a fraction of a milli electron volt or something. So again, the corresponding resolution has to be selected so that you can find what are the changes that you are looking for. A monochromator or crystal analyzer is 2 cot theta d theta. We worked it out. This is very simple. You have 2d sine theta equal to lambda, and if you differentiate it, then you will get that d lambda by lambda equal to cot theta d theta. Okay, lambda equal to 2d sine theta. So lambda is proportional to sine theta, and so therefore d lambda is proportional to cos theta, and d lambda by lambda will be cot theta d theta. And the energy, as we know, is 1 over lambda square, proportional to 1 over lambda square. The corresponding energy resolution is 2 cot theta d theta. Okay, whereas 2 theta is a Bragg angle. All right, so this is how it comes, and therefore we'll just work out what are the typical resolutions that are possible. And so that's another important quantity. Yeah, and you can see that very clearly. If you use a low, even for a given value, if you are able to choose a proper monochromator so that the EI is small, then DE will also be small, and so you can get a better resolution if you use a smaller energy. That's a general conclusion again. So these are certain things. Then now, the next issues are depending on the wave vector and neutron, the phonon wave vector and the phonon displacement vector or phonon eigenvector. There are various names. You can call it phonon polarization vector or phonon eigenvector. Essentially, it gives you the displacements of atoms during a vibration. So, depending on Q and the eigenvector, one has to choose a scattering plane for measurements. Now, what does this mean? Quite often, the spectrometer we have a certain plane in which we are working. That's a horizontal plane. Okay, this diagram is all in the horizontal plane. It's not vertical; it's in the horizontal direction. So you have neutrons coming in, and these all the arms are in the horizontal plane. So suppose if I put my crystal in such a way that let's say uh, the reciprocal lattice vectors A star and B star are in the horizontal plane, then I say that okay, I'm in the A star B star plane, and my Q as well as uh, the eigenvector, the displacements that will be seen will be all in the that plane only. For the simple reason that because capital Q is what we actually measure is the dot product of the capital Q, that is a wave vector transfer, that is G minus Q, dot the eigenvector. So it's only that component is. These terms have to be in the plane of the instrument or in the plane of the crystal, both have to be the same. And any displacement which is perpendicular to the plane of the instrument obviously will not have a contribution apart from the resolution. There is always a small vertical resolution. So to that extent, even the vertical components will contribute. See, remember, we don't measure an exact Q and exact omega, but there is always a resolution d omega, dq and d omega because of various terms, and so the measurements are all integrated within the resolution. However, clearly the vertical components, the components which are not in the plane of the spectrometer or in the plane of the crystal that we are measuring, yeah, essentially the plane of the spectrometer, those components will not be seen. So if you want to measure the dispersion curves in a different direction, the crystal may have to be reoriented. Okay, so we have to choose a scattering plane, and so suppose it is the A star B star plane or whatever plane it is. It need not be just that, but once a plane is chosen, one has to align the crystal in such a way that that particular scattering plane of the crystal is comes in the horizontal plane uh, of the spectrum. Fine. So that has to be done. Then one has to choose what is the range of energy and wave vector over which the measurements will be made. So these have to be estimated from whatever knowledge or experience one has about the sample, about the crystal. So, for example, if I already know what are the elastic constants, then you probably know that the elastic constants are actually the slopes of the acoustic formulas. Okay, so for the square of the elastic constants are related to the square of the slope of these dispersion curves. Okay, d omega by dq. If I take a d omega by dq at the near the origin, then these various longitudinal and transverse phonons have those whatever slopes are there uh, can be multiplied with the density of the material, and so the elastic constants are proportional to rho times v square. V is the velocity of the phonon. This phonon velocity here is nothing but d omega by dq. It's like the sound velocity corresponding to that phonon. And so these are, so that means if I know the elastic constant, I can estimate, calculate what are the slopes. And if I know the slopes, I can predict the frequencies at least near the origin of the Brillouin zone. So at least a linear part of the acoustic phonons is very easy to predict the frequencies, and so one can make measurements to confirm those values, and then whatever temperature or pressure dependence one might be interested in. On the other hand, if I already know the Raman frequencies or infrared frequencies, those correspond to the frequencies of the optic phonons, and these optic phonons, well, then at least some of these optic phonons may be known from optical experiments, and if those numbers are available, it becomes again a good starting point for phonon measurements. Those will be at the zone center. So that means the slope of the acoustic phonons and some of the optic phonons one can get from other experimental data. And yes, so that, and of course, on the whole, it's good to have lattice dynamical calculations of the structure factors so as to choose what are the right values of G, the reciprocal lattice vectors, and also the right expected values of the frequencies and so on. So these are these are the various steps for measurements of the phonon dispersion curves. Okay. Now, at this stage, there is one important question that was raised the other day. Let us just look at that. That is the effect of the resolution ellipsoid. So, okay. Right. So, uh, let's take typically. Okay. Suppose let's say I want to measure this phonon. This is omega, and this is q. Now, to this, I can do a constant q scan. So I can scan at different points like this. Okay, along this line, the small q is fixed, and the g is also known fixed. Therefore, the capital Q is fixed along this line. That is called a constant q scan. And so these different points will correspond to different omega. Okay, each corresponding to different values of the energy transfer. So this is how you measure it. Now, what is the effective resolution? Uh, See, we have a resolution ellipsoid, and suppose that resolution ellipsoid is like this. Then what I would measure here is the overlap between the resolution ellipsoid and the dispersion surface. Okay, so clearly it is zero here. I won't see any intensity. But as I go for further, uh, okay, and let's assume that is so. Let's say the moment you are here, you guess so that would be resolution ellipsoid. You get something, then and so on and so forth. So at every point, it is the integral between the resolution ellipsoid and the dispersion surface. So you can expect the intensity to go like that. Okay. But now we know one important thing, namely that the intensity, if I say as a function of omega, is related to the phonon population term. Okay, for the neutron energy loss, it is this one. Okay. Now, so now, but this there is a role of temperature here. So let's say if my frequency is sufficiently large compared to kT, okay, and the n you know is 1 over e to power h cross omega upon kT minus 1. Okay, so if omega is small compared to kT, then this quantity would be uh, this should be 1 plus h cross omega plus kT, and 1 would cancel. So that would be like kT over h cross omega. Okay, under that condition. So now so in that case, my I omega would be proportional to temperature. Okay, because h cross uh, uh, no, this is n, and there's a okay. Sorry, there is another term here. Okay, there was also a omega square. Yeah, I omega had this term. So actually, omega was in the denominator. Uh, just to remind you, yeah. So it's n plus 1 divided by omega. Actually, it's n plus 1 h pro. Okay, so omega is in the denominator. That's what we wanted to say. Okay. So, okay. So that is what you end up getting 1 over omega square. Now, on the other hand, if your h cross omega is larger, sorry, it's smaller than kT, that means at high temperature. This is at low temperature. You have a omega square dependence. Right? Yeah. Okay. And if h cross omega is much, oh, sorry, it's missed up. Uh, this, I can write it as 1 plus h cross omega if omega is small. So actually, it should have been the other way. If h cross omega is smaller than kT, then h cross omega upon kT is much less than 1, and therefore this term can be the exponential h cross omega upon kT can be written as 1 plus h cross omega by kT, and so that is how this comes up. So this is actually, I'm sorry, this is not at low temperature but high temperature. Now, if at high temperature you have 1 over omega square, and for low temperature, when temperature is much smaller than h cross omega, then your n becomes then this is omega is large, and therefore the my term e to power h cross omega upon kT uh, is uh, is anyway much greater than 1, and therefore I can ignore this minus 1, and therefore your n will become proportional to uh, okay, so that's in the limit, this becomes an extremely large number, and therefore uh, this intensity I omega is simply proportional to the n is a very large number. Okay, that's and therefore it just becomes proportional to 1 over omega. Okay, so in fact it can be shown that so at low temperature you have a 1 over omega dependence, high temperature you have 1 over omega square dependence. But now what is the use of this for the resolution? So now what happens here is that in this part of the resolution ellipsoid, there is a greater weightage of smaller frequencies. So it is not symmetric with respect to the your middle point, but there is a larger weightage of smaller frequencies, and therefore this peak will actually not come at your the correct or the correct frequency might be actually somewhat higher. That is the omega 0, and then what you actually measure would be slightly lower because there is always greater intensity for the smaller frequencies. So there is a because of the resolution, you can have a shift in the measured frequencies. Again, it depends on your dispersion surface and so on. So there is this thing one has to be concerned with. Okay, there is also a role for momentum. See again, I of omega. Remember, there are terms like e to the power minus. There is a revival factor times there is a q square term also. So besides other terms, so that is in the structure factor. Now, so that means the intensity has a q dependence, and once again, if your q is small, then this term will not be very important, and therefore, generally you can expect larger intensity for larger q, and again because of that, you have a higher weightage of larger q values, and therefore your frequency or the wave vector of your selection might be so. Okay, so that would be relevant if, whenever again you are making a measurement. So if you are thinking that you are making a measurement around q0 and omega 0, your actual measured value might correspond to a q which is the q peak might be slightly larger than your q0, and as we just explained, your omega peak may be slightly less than your omega 0. So there are resolution corrections like this. There are also issues because the resolution tends to be quite asymmetric. We often choose a poorer resolution in the vertical direction. So Q, which is in the perpendicular to the plane of the measurement, that is in the vertical direction, that value of the resolution is usually quite large because you want to get as much intensity as possible. And but if your dispersion surface is not is somewhat asymmetric, then one needs to be concerned about these aspects also. So these are some of the issues related to the dispersion. Okay, let's look at a few problems now. Okay, this is a very simple problem we start with, that if my suppose my incident wavelength is just 1 angstrom, and I want to measure a phonon which I know from, let's say, Raman scattering is about 33 centimeter inverse. Okay, that's a Raman known values of the frequency. So I just like to know that if I scatter my neutron with such a phonon, then what are the expected values of the scattered neutron? What is the scattered neutron wavelength, for example? This is just, and if the scattering angle, okay, here this is a smaller one, but if the scattering were at, say, for example, 90 degrees, then what are the corresponding Q values? Okay, so let's try to do this very simple problem just to get going. Or we can. Okay, so here see, we know that if my lambda is 1 angstrom, then the energy let's say lambda I. The corresponding EI is 82 upon lambda square, 82 being the milli-electron volts, so it is 82 milli-electron volt. The phonon energy is 33 centimeter inverse. So if you convert into the phonon frequencies, you multiply by the velocity of light, and so this will come out to be 1 terahertz. Okay, so multiply by 3 into 10 to 10, so you get 10 to the power 12. And corresponding to this number, okay, so omega is 2 pi mu, and the energy of the phonon, which is h cross omega or h nu, is equal to, if you write in terms of energy units, please try to do it yourself, is 4.1 milli-electron volts. Okay, so the phonon energy is this, my incident neutron energy is 82 milli-electron volts, and therefore, for neutron energy loss, EF will be EI minus h cross omega, or E, what you have here. So that would be 78 milli-electron volts. Okay, so now that means for this again, if I have to get the wavelength, my lambda f will be 82 divided by lambda f square will be 82 divided by EF. Okay, and so if you put it, this will come to about 1.025 angstroms. It is simply 82 divided by 78. So that's what number we normally get. Sorry, it's like, yeah, actually it's, I've jumped here a little bit. And so I will take a square root here. Square root of this number lambda f will be 1.0 angstrom. Okay, so that is how we can work it out. Similarly, you can check it up. If it were a neutron energy gain, that means EF could be greater than it was minus greater than this, so it will be EI plus EF. So you can have a definition. Okay, so for the neutron energy gain, you have to sum it up. So 82 plus it will become then 86, and therefore in that case lambda f would be would become, instead of 1.95, it will be 82 divided by 86, so it will be 0.95, and the corresponding lambda f would be less than 1, so 0.975. Okay, so that would be a lower number. If I just plot it schematically, let's say corresponding to on the omegas, okay, you can even go to the lambda f. That is the value same as lambda I. You can have a inelastic scattering on either side. So this is 1 angstrom. This would be like 1.025 or 0.975. Okay, so this neutron energy gain and neutron energy loss, Stokes and anti-Stokes both sides. Now you can see that actually these are extremely small changes and would require then a fairly good resolution. Quite often the instruments we work with may or may not have this kind of a good resolution. So then if you have to actually measure a phonon which has an energy as low as 4 milli-electron volts, then you would not choose a incident neutron of such a small wavelength, large energy. You would like to choose an incident neutron energy, which is smaller than this. Therefore, so that these phonons can be measured with the available resolution. We'll just work out that how come this resolution. This for the incident neutron energy of 80 millielectron volts, this requirement of about 5% energy changes are comparable to the typical resolution we actually have. So it's not much better than that. Okay, then the other question was we'll calculate the Q corresponding to this scattering angle 90 degrees. So let's look at the Q part. All right, so we want to look at the Q. And so as far as the Q is concerned, Q is vector Q is vector Ki minus Kf. And so you can see that the magnitude of Q square would be Ki square plus Kf square minus 2 Ki Kf into the cos of the scattering angle. Let's call it theta s. Okay, it's simple vector algebra. If you want to just want me to write it formally, then it is Ki square plus Kf square minus 2 Ki dot Kf, and that's about it. Now, so if theta s is 90 degree, then this term just goes to 0, and therefore Q square is about Ki square plus Kf square. And as you just found, Ki and Kf are nearly equal, just about 5% different. We just calculated. The two wavelengths are like 1 and 1.025 angstrom, and therefore the squares will be nearly similar. So this is roughly equal to 2 times Ki square. Okay. Now let's see what Ki is. So the Ki equal to 2 pi by lambda. So this is 2 pi times lambda is 1, we said, so this 2 pi angstrom inverse. Okay. So and Ki square is 4 pi square, which is roughly 40 angstrom inverse. Or well, I will not really do this. So let me rather say here, what is here, the magnitude of Q is root 2 times Ki. And so therefore, if Ki is about 2 pi, that is around 6, and 6 multiplied by root of 2. So that will be about 9 angstrom inverse. So the value of capital Q is 9 angstrom inverse, corresponding to if we have the situation where the lambda is 1 and lambda energy transfer is as little as this. So this is actually quite high value of momentum transfer or electric transfer. Why I say high is it will just come shortly in another problem. Okay. Okay, good. So let's move on to the next another. Yes. Okay. Okay. There's another simple problem. Let's try to work it out. In our triple axis neutron spectrometer, we have a monochromator that is copper, and we use a break plane which is 111. HKL indices are 111. So that's and for this particular value of the HKL index, you have certain value of the de-spacing and so on. So the problem we are looking at is, suppose, so that's the plane we have, and let's, for simplicity, assume that the lattice constant of copper is 4 angstrom. It's a cubic crystal, so you can, that would be easy. And so with this value of the lattice constant, we want to know what is the resolution in EI and EF corresponding. If I have, suppose my EI is 20 millielectron volts or 80, we just try to solve, numerically get these numbers. Okay. So okay, this is a fairly interesting problem. So how do we address this? Uh, my de-spacing for this copper 111 uh, is equal to A divided by square root of h square plus k square plus l square. So that will be everything. Okay. So that is 4 upon root of 3 angstroms. Okay. Now we have 2d sine theta equal to lambda. So if I've already given, let's say, I want to choose a value of lambda such that EI is 20 or 80. Let's start with this number. It is a little simpler. Then we just said that if we had seen this, that if my energy is 80 millielectron volts, then the corresponding lambda is lambda square is 82 by E. So let's say this is about 1. You can do a more accurate calculation, but here just to illustrate, so lambda square is 1 angstrom square. Okay, if lambda is about 1, then and d is known. So I would know what is my sine theta. Sine theta is lambda upon 2d, and that is d, and therefore you can see that that will be root of 3 divided by 8. Okay, that is the value of sine theta. Typically, numerically, how much it is? Root of 3 is about 1.7 divided by 8, so this is roughly 0.2. And you know, sine theta of 0.2 is about 0.2 radian. So theta is roughly 0.2 radian, or you can say about 12 degrees. So for this particular crystal, to get choose a neutron energy of 80 millielectron volts, my Bragg angle would be as little as 12 degrees. Okay, so that's about it. And the corresponding sine theta is lambda by 2. Now we just said what is the resolution. Resolution in energy is 2 cot theta d theta. Okay, so now let's see what is cot theta. I need to calculate cot theta. So if I have sine theta, then in fact you can easily look it up. Cot theta would be approximately 1 over sine theta, because cos theta would be close to 1, and therefore that would be like 8 over root of 3. Okay, inverse of this. So that is what you get. And if that is what I get, then my corresponding energy resolution is twice of this, that is 16 divided by root of 3. And so 2 cot theta is this multiplied by 2. And 16 divided by root of 3 is, you find, so it is close to 9. Okay, 16 divided by 1.7. So it will be something like 9 or 10. Okay, so my d EI upon d EI which is 2 cot theta d theta, comes to about 9 into d theta. Now, how much is d theta? Typical value of d theta, that is the angular divergence of my beam. So, what it really means is that if you have a crystal and you take a incident beam and the reflected beam, there is always certain angular resolution involved. So there will be certain angular resolution from various reasons. So there is a d theta, and the d theta is typically 1 degree. Okay, that's a typical number we talk about. And 1 degree is in radian is about 1 by 60. 1 degree is 1 by 60 radian. So you would write here 9 multiplied by 1 by 60. So that will be about 0.15. So you can see that d by e is as large as 0.15 or 15%. But this is a particularly poor resolution situation. You start with a very high energy, and you start with very high energy, and therefore the theta is small. High energy means small wavelength, and a small wavelength also means a small theta, and a small theta means very large cot theta. Okay, so what we are saying is that for large energy, smaller wavelength, smaller Bragg angle, and therefore a poor resolution is what we have. Well, why do you use a poor resolution? Quite often you use a poor resolution because you want to maximize your neutron intensity. So you can get a very good intensity if you have you use a poor resolution. And again, as we said, depending on the requirement of the experiment, I need to tighten the resolution. I can tighten it by two means. I can tighten it by tightening the angular combination, or I can go to lower value of energies. So let's just work out. If it's a smaller energy, what will happen? So that's something simple here. I will just so if I use my if I calculate for 20 millielectron volts, then it's a energy. I'll probably move a little faster. So here you can find that your lambda I would be about 82 divided by 20 lambda square. So that will turn out to be about 4 and lambda about 2 angstroms. So I purposely wrote it here. This corresponds to 1 angstrom. This corresponds to 2 angstrom. So 1 angstrom we have already done. If I do lambda 2 angstrom, then again if I use the same relation of my Bragg angle, and if it is 2 angstrom now, my sine theta would also be the double of what I had earlier. Sine theta would then be, instead of root 3 by 8, it is root 3 by 4 now. Okay, and the corresponding the Bragg angle would be now also double, close to that. The corresponding cot theta will be now would be halved compared to what we had earlier. And so I'm going to jump steps here. What you find is this is instead of 9 now, this is more like 4. Okay, so the dEi upon dEi now becomes 4 times d theta, which is 1 degree or 1 by 60 radian. And so that would be, it will be instead of, it would now be reduced, what did I do right? No, this is not correct. Sorry. Sin theta is root 3 by 4, and cos theta equal to square root of 1 minus sine square theta, so 3 by 16. And then this would be root of 13 by 4. So cot theta is 4 upon root of 13, sorry. Okay. So, yes. Okay, that is cot theta. And just like it properly. 2 cos theta 2 theta. So that would be 2 times 4 upon 2 to 13, and theta say something like 1 by 60. So that roughly will be so let's say so, okay. So divided by root of 13 is about 3.6 times 15. So that would, finally this is it will be of the order of 0.04 or so, around there. Okay. So this is or is it different? Mm, no, so this sorry, this is a little bit larger. Okay. Okay, so anyway, I think you can revise this number, but the whole idea is that now with the energy which is wavelength which is double, we could improve on the resolution substantially, and so now we have a better resolution. Okay, this is coming more like 5% or that kind of a number. Uh, Similarly, if we have a graphite crystal, then yeah, please do it numerically properly. If we have a graphite crystal which is yes, if we have a graphite crystal, here the lattice constant, C lattice constant is about 7 angstrom, and therefore the d spacing, unlike which is here, the main difference is in terms of the d spacing. So for copper, the d spacing was a by root of 3, which is 4 by root of 3. So it was around 2, 2 angstrom, a little greater than 2. Whereas for pyrite graphite, the d spacing will be C by 2, and that will be about 3.5 angstrom. So the d spacing is much larger. Now, if your d spacing is larger, then the correspondingly sin theta is which is lambda upon 2d is smaller. It tends to be not half but substantially smaller than copper. And as we said, if the smaller is the sin theta, the larger is so. Okay, what we have is if your d is smaller, okay, if d goes down, then Sin theta goes up and cos theta goes down, and so your dE for E also goes down. So you can improve your resolution if you use a smaller spacing. Okay, so therefore copper gives a better resolution than graphite. On the other hand, graphite has a much better reflectivity, and also the energy range it gives is different, and so quite often we use then graphite. We use graphite although the d by E is smaller, but we use for a very small energy. Typically, graphite is used around 20 millielectron volts or mostly around 15 millielectron volts for certain reason that we can remove the second order by appropriate filter. So that is the main reason that we use graphite around 15 volts. In fact, graphite is used around 15 or also around 30 because at that energies, second order reflection contributions of the Bragg reflection, those neutrons can be avoided by putting a filter. Copper is used. So in actual experiment, we start with a higher value of incident energy and then higher, and EF which is lower. So therefore, copper is used here and Kg is used here, and we try to match the resolution. And these resolutions will be typically in the range of 5 to 10% from copper, and similarly also 5 to 10% from pyrolytic graphite. And so that the net resolution, what you have from your for your measurements will be contribution from DEI by EI from the monochromator and DEF to EF in the analyzer, and it is the sum of squares average. So in fact, approximately your net dE by E would be the square root of, it's not exactly the case, one has to see the proper correlations, but it's approximately, that is a thumb rule one can use. Okay, if they are not, see the point is if the two functions, monochromator and analyzer, if they were not correlated, then you could simply take the square of the two and take a square root. So if this number is, each of the number is in the range of 5 to 10%, then my net also would be around 10%. So that is the net 10% energy resolution is what we end up getting. So for these levels of energies, our resolutions are in the range of 2 to 5 MeV for the dE by E. Or sorry, dE itself. That is the resolution on the phonon energy would be in the range of 2 to 5 millimeter volts for these kind of settings. Okay. Okay, let's quickly move very another very interesting problem that is now on the structure factors. So what we'll try to do is, suppose we were to measure phonons in a simple structure like sodium chloride, then what are the G vectors, for example, one could try to measure. But if I want to calculate what are the structure factors for these G values, let's try to work on it. Okay, so we're going to do that. We'll assume certain scattering lengths, and but before we do this, in fact, it's a lot of there's a lot of physics here. See, a structure like sodium chloride, you know that it is a face-centered cubic, and the basic cell has a basis of two atoms. A primitive cell, let's say one sodium at located at 0, 0, 0 of the cubic with respect to the cubic axis, and chlorine at half of half. Okay. In fact, there are in the cubic unit cell, you have four sodiums and four chlorines, but in the primitive cell, you have one each of them, and therefore there are two things. Once it is a face-centered cubic, then we know that the G values are allowed G values are only those in which the sum of any two of them has to be an even number. So because an FCC lattice has a reciprocal lattice which is a body-centered cubic, and so only those. So there are certain allowed G values that you are already aware of. Okay, certain reflections are missing for sodium chloride, and so only certain reflections are allowed. So, for example, we know that 100 is not allowed, but 200 is allowed. So, if you have HKL and H odd, that will not be allowed. So, only this reflection exists, but these two don't. In fact, these two values actually happen to be at the Brillouin zone boundary and not at the Brillouin zone center. So, that is at the zone center, and this is at the zone boundary. That's one. Similarly, 111 happens to be at the zone center. That's an allowed reflection. Okay, so we are aware of these kind of things. Okay. Now, as far as the structure factor for Bragg reflection is concerned, the essential terms would be the scattering length. What we have is okay. For convenience, I'll forget about the Debye factor, and therefore, so it is the coherent scattering length times e to the power g dot uh, r of k, that is the coordinate of the atom, and sum over the two atoms. So we have the two terms, and so if you write it, it will be B sodium and Rk being 0, 0, 0, so you will have base term will be 1 plus B chlorine and e to the power I 2 pi. So what we have is 2 pi H into half plus K into half plus L into half. So if G is HKL, that's what we're saying. Yeah, what is it? G is equal to HKL. Okay. So this is nothing but VNA plus VCL times e to the power I pi H plus Q plus L. Okay, so that is a structure factor for a Bragg reflection. Okay, and on the top of it, you have further conditions coming from the face-centered cubic lattice. That certain values of HKL only are allowed. So what I'm saying is, even for those values which are allowed, uh, there is a structure factor, and if both were equal, okay, there are some small differences between these neutron scattering lengths of sodium and chlorine. Or even if you were doing X-ray reflection, X-ray Bragg reflections, still the corresponding form factors for the two atoms are different. So those have to be considered. In fact, in a very simple case, if the two atoms were identical, then you will find that for certain HKL, this term will become 0. For example, for 111, if it were 111, then that this term would become -1. So it will be Na minus BCl, for example. Okay. So for 111, this would become just Na minus BC. Which would measure is only the difference in the scattering length quantity. Okay. The actual intensity is proportional to the square of the structure factor. Now, if you have a phonon, then what happens? So, I need to. So these would still be valid, but in case of phonon, or maybe I can. See now, if you have a phonon, and then I purposely chose a capital Q is almost like G, but a little bit different. It's almost equal to the capital Q. If you have a transverse phonon, let's say you have a transverse acoustic or transverse optic phonon, then my displacement vectors are perpendicular to this. So they are perpendicular to the x direction, perpendicular to the a star direction. Okay, which happens to be x direction also in the Cartesian system. Now, so if xi is perpendicular to this, and if I'm looking at q dot xi only, because that is what my intensity will be proportional to. Therefore, if q is parallel to a, then that would just go to 0. So uh, that is a quantity. Okay. So if my g is in the x direction, then I will not be able to see the transverse phonons there. On the other hand, if these are longitudinal phonons, then xi is parallel to a star. Okay, so that is assuming that g is parallel to a star, like 200, 300, or then q dot xi will be 0. It may be 0 because of some other phase factors, but not because of this. Okay. Now the displacement is the x, y, and z component of sodium, and also x, y, and z component of chlorine. Okay, and therefore now here I have to introduce, apart from these two terms, also another term, that is q dot psi, to get the, instead of the Bragg structure factor, if I have to use a one phonon structure factor, then I have to introduce this two. Okay, so now that extra term will come, and therefore I have to have okay, q dot xi, and so q dot xi here will be equal to the xi, only the x component x here I would multiply with xi of sodium, and here I would multiply with xi of chlorine, the corresponding x components. So this is an additional. So you see, apart from this phase term, I now also have another terms here, if they are equal or unequal. Okay, if they were And that is, remember, there's another term here. I have to also worry about dividing it by the square root of mass. So this is further there is a division by square root of mass also of sodium and square root of mass of so stir factor for the diffraction, let me just again rewrite it. This is like 1 plus, or rather, B sodium plus B chlorine e to the power I 5 H plus A plus L, and structure factor for one phonon E sodium divided by square root of mass of sodium into A2 here that will make a difference plus B chlorine mass of chlorine into and the same test. Okay, fine. So now let's take a, we already said for transverse phonons, these terms will just go to 0. So well, it depends. I mean, not we can measure transverse phonons by choosing a proper Q direction. But so now, for the sake of example, if my Q is 200, then let's see what happens. If Q is 200, then how this will simplify? This will simplify as that's as far as this term is concerned, and what I just said, my small q is a small number, and for acoustic phonon, these two xi Na and xi Cl will be like you can say like +1 and +1. Okay, both are equal. Uh, so that means for this case, these two terms become similar, and the only change we have compared to the Bragg is that the mass term here, but otherwise the phase is similar. Okay, so what we found is that for the acoustic phonon, we have a situation similar to f of q turns out to be similar to s of or f of q or yeah, similar to it. Okay. However, if you have the optic phonon, this is let's say 1, and then so for optic phonon, this will be like +1 and -1. Then you will get in the minus term here, and so then these are quite different. For the Bragg case, you have the two terms. There is a plus sign in between, and for the optic phonon case, it is a minus sign here. Okay. Now, if I were to just take two specific examples, so for 200 anyway, you don't really see a problem, because for 200, this term just becomes 1, and therefore you have plus and minus 1 is all that you get here. So so for 200 in particular, the S of G will be B sodium plus B chlorine, and here it will be B sodium divided by square root of mass of sodium plus B chlorine divided by square root of mass of chlorine. So that is for the yeah, this term and this term. Okay. That is for the acoustic phonon. For optic phonon, that becomes minus. So this remains the same, but you can see that for the optic phonon, this intensity you lose considerably. But then you might wonder, where do I measure the optic phonon then? How can I measure it? Because obviously at this point, the intensity would really be very small. So for optic phonon, you can see that what I really want is that this term should become uh, not +1 but -1. In that case, I can get a change of sign here. So if you look at a G, which is something like 111, if you do that, then uh, then what will be the case here? This corresponding to 111, it is e to the power I 3 pi, so that is -1, and therefore my S of G will become VNA minus BCL. Okay, so that tends to be small. However, for phonons, for acoustic phonons, you will get here. So for acoustic phonon, it is VNA minus BCL divided with the corresponding mass. Whereas for optic phonon, I get a plus here, and so I can get a large intensity for the optic phonon for this G, and so this can be measured. Okay, so maybe you can try to do a little better for various this situation. You can try to understand a little better. If there are questions, please let me know. Okay, so if I come back to the question here, one answer would be that 300 is anyway not a zone center phonon. It is a zone center, a billion zone center. This is a zone boundary, so there is no question of measuring these phonons here. But at 200 and 400, you would measure the acoustic modes, the longitudinal acoustic modes, and that's all. Whereas if you want to really measure the longitudinal optic modes, then you need to go to points like 111 and so. Now, yes, I okay. There are some remaining things. Maybe we can come back to it later. So I okay. So that was it for phonon density of state. There was no real issues. But it just give a problem for you to look at. So please try to do this. Again, if you have a phonon density of state in the range of say 0 to 80 millineutron volts, in that case, please see what are the typical Q ranges where these measurements can be made. And if you know those Q values, I can give you an answer here. This will be the maximum Q you can get will correspond to the will be about 12 angstrom inverse. Let me just very quickly write an answer here. So you see, we said that Q Q square equal to is of the order of okay. So anyway, I mean you have to assume what is your EI and what is your EF, and then correspondingly get KI, KF, and KI and KF, and then write Q square. So you will get numbers which are in the range of say 10 angstrom inverse. Okay, it will be some range over this. It can be as small as 0 also. And if you have a U square this, then you have a divided factor which is e to the power minus Q square U square, and the various terms. So that is proportional to the, and if you write terms like this. That is proportional to the elastic term, and these are proportional to one phonon and the multi-phonon and so on. You can also try to calculate if for a given system, suppose if I know what is the frequency and what is the mass of the oscillator, essentially these are simple harmonic oscillators. So if you know the angular frequency and mass of the simple harmonic oscillator, then you can work out what is u square, that is the root mean square displacement of the atom, and using the total energy equal to n plus half h plus omega, you can work it out, and you can see how it's related to temperature. In fact, you find that if I plot u square as a function of temperature, then it's actually something like that. You have a 0 point energy and some larger number. So, but please try to calculate, assuming some typical values of frequency and mass, what are the u square. You can assume that say mass equal to 16 for oxygen, and assume a phonon energy of, let us say, about 25 MeV. Okay, so for these settings, try to calculate what are the u squares. So with this, I will leave it today. I think we are coming to a close, and Monday then we will maybe continue with the quasi-elastic neutron scattering, the molecular dynamics simulation, and some tutorial for those items. Thank you very much. Now, Dr. Vasu will make some announcements, so please tell me.
Hello, everyone. Please note that the assignment regarding magnetic neutron scattering, this has all been uploaded into Anuvidya. So those who want credit, please download, solve it, and submit it. In Anuvidya, it has been already uploaded. Thank you, and have a good weekend, and see you on Monday.